Exploration is not a choice, but a necessity for human survival. Buzz Aldrin. Stars, planets, galaxies. Makes up only about 5% of the universe. The rest, 95%, is invisible. And most of that is something called dark energy, which alone accounts for roughly 68% of all that exists. The discovery of dark energy was a genuine cosmic surprise. In 1998, astronomers observing distant supernovae noticed something astonishing. The universe's expansion wasn't slowing down under gravity, as everyone expected. Instead, it was accelerating. Galaxies weren't just moving apart. They were racing away from each other at increasing speeds. Today, the universe expands at roughly 70 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, galaxies recede about 70 kilometers per second faster. To explain this unexpected acceleration, scientists coined the term dark energy, a placeholder for an unknown, repulsive force. Some proposed it behaves like anti-gravity, reversing the attractive pull of ordinary gravity over cosmic distances. Others suggested it could be a form of vacuum energy, a strange property of empty space creating a negative pressure that drives the expansion. Ironically, the concept goes back to Einstein, who introduced the cosmological constant in 1917 to balance gravity and keep the universe static, a move he later called his biggest blunder. Now, more than a century later, that idea is at the heart of modern cosmology. Unlike matter, which forms stars, planets, and galaxies, dark energy is uniformly distributed, filling every cubic centimeter of space. It doesn't cluster, it doesn't condense, it simply exists everywhere, quietly pushing the cosmos apart. Scientists can measure its influence through cosmic microwave background fluctuations, gravitational lensing, and the large-scale distribution of galaxies. Despite knowing its effects and estimating that it makes up 2/3 of the universe, we still have no idea what dark energy really is. Do black holes really evaporate? In the 1970s, the late British physicist Stephen Hawking proposed a shocking idea. Black holes aren't eternal. They emit radiation and can, in theory, evaporate completely. Here's how it works. Quantum mechanics tells us that empty space isn't really empty. Instead, it's bubbling with pairs of particles and antiparticles that constantly pop in and out of existence. Normally, these pairs meet and annihilate each other almost instantly. But near a black hole's event horizon, the boundary beyond which nothing can return, something strange happens. If one particle of a pair falls into the black hole while its partner escapes, energy conservation requires that the infalling particle carries negative energy, effectively reducing the black hole's mass. The escaping particle carries positive energy, radiating outward as what we now call Hawking radiation. Over unimaginable timescales, far longer than the current age of the universe, which is roughly 13.8 billion years, this process slowly chips away at the black hole, causing it to evaporate. But here's the mind-blowing part. Recent research suggests that black holes might not be the only objects capable of this evaporation. A team led by astrophysicist Heino Falke at Radboud University, using equations inspired by the Schwinger effect, found that any object with mass can, in theory, produce Hawking-like radiation. This includes stars, planets, and even everyday objects. Yes, your coffee mug emits it too. Though the effect is so tiny it would take trillions upon trillions of years to matter. The physics behind this is astonishing. In quantum terms, particles have a cloud of probabilities describing where they might be. When gravity tugs slightly on one particle but not its partner, their clouds don't overlap perfectly, preventing annihilation and producing radiation. Essentially, gravity itself can pull energy out of the vacuum of space. Of course, this remains theoretical. Current technology can't detect such subtle radiation from ordinary objects, and some physicists remain skeptical, arguing that Hawking radiation is unique to black holes. Still, These calculations push the boundaries of our understanding, hinting that evaporation might be a universal process, not just a cosmic oddity. Neutron stars are so dense that atoms collapse into pure neutrons. Neutron stars form when stars at least 8 times the mass of our Sun reach the end of their lives. After exhausting their nuclear fuel, the star's outer layers explode violently, while the core collapses under gravity. This collapse is so intense that atoms themselves cannot survive. Electrons are forced into protons, creating pure neutrons. The result is a star that's essentially a single giant atomic nucleus, about 20 kilometers in diameter, but packing more mass than our Sun. To put that in perspective, imagine compressing Mount Everest into the size of a sugar cube. That's the scale we're talking about. The densities inside neutron stars are almost incomprehensible. A sugar cube-sized piece would weigh 100 million tons. The pressure is so immense that matter behaves in ways completely alien to our everyday experience. Neutron stars are held up against further collapse by the strong nuclear force, which binds neutrons together in the star's core. But if a neutron star exceeds roughly 2 to 3 solar masses, even this incredible force cannot resist gravity, and the star collapses further into a black hole. Neutron stars also spin at mind-boggling speeds. Some rotate hundreds of times per second. These spinning neutron stars emit beams of radiation from their magnetic poles, observed from Earth as pulsars, cosmic lighthouses ticking with clock-like precision. Their magnetic fields are trillions of times stronger than Earth's, warping space-time and accelerating particles to near light speed. A neutron star's surface gravity is so intense that a paperclip dropped from 1 meter would hit the surface at thousands of kilometers per hour, instantly vaporizing. Inside these stars, matter exists in exotic states. There may be superfluid neutrons, strange particles called quark matter, or hyperons heavier than neutrons. Some theorists even speculate about nuclear pasta, ultra-dense layers shaped like spaghetti or lasagna, formed by competing forces inside the core. Each neutron star is essentially a natural physics laboratory, allowing scientists to study matter under conditions impossible on Earth. What are magnetars? Picture this. A magnet so strong, it could rip the electrons out of your atoms, twist matter into razor-thin spikes, and wipe the memory of a spacecraft like it never existed, from thousands of kilometers away. That's a magnetar for you. A cosmic beast with a magnetic field 1 quadrillion times stronger than Earth's. 1 quadrillion. To even imagine it, forget everything you know about magnets. This isn't science fiction. It's the universe flexing. Magnetars are the rare cousins of neutron stars, the remnants of massive stars that exploded in supernovae. Neutron stars already cram more mass than our Sun into a sphere barely 20 kilometers across. But magnetars, they take the absurdity up a notch. Their magnetic fields are so intense that atoms, which normally look like little solar systems with electrons orbiting a nucleus, collapse into needle shapes, warped and stretched beyond recognition. Matter itself bows to the magnetar's will. And it's not just about atoms. These stellar monsters unleash bursts of energy that make our Sun look like a candle. In milliseconds, a magnetar can release as much energy as the Sun produces in 100,000 years. Gamma rays, X-rays, plasma storms. If one pointed at Earth from a few thousand light years away, it could fry satellites, scramble electronics, and temporarily dance in the sky as a ghostly aurora. These aren't hypothetical warnings. Magnetars are real, and the universe has given them superpowers that make even black holes look tame in comparison. Yet, despite decades of study, magnetars remain enigmatic. Why do only some neutron stars become magnetars? How do they generate these insane magnetic fields? No one knows for sure. Some theories suggest that the fastest spinning cores in collapsing stars kick their magnetism into overdrive, but we're still groping in the dark. Every magnetar is a riddle wrapped in a cosmic enigma. Imagine holding a teaspoon of magnetar material. On Earth, it would weigh millions of tons. And if you somehow dared to stand near one, which, spoiler, you can't, your atoms wouldn't just feel the pull. They'd shred, stretch, and realign, becoming threads of pure quantum spaghetti. The universe is weird. Really. When astronomers first started spotting planets beyond our solar system, the universe suddenly felt way bigger and way weirder than anyone imagined. We now know of thousands of exoplanets, and some are straight up alien. Take the diamond worlds, for example. Extreme pressure has squished carbon into solid crystal. Picture a planet with rivers of sparkling diamond, mountains glinting like giant gemstones under some alien sun. Yeah, it's basically the universe showing off. Then there are the magma ocean planets, where the surface isn't solid at all, but a boiling sea of lava. These planets can be hundreds or even thousands of degrees hotter than Earth, with volcanic activity so insane that entire continents could be molten rivers of fire. Walk there? You'd literally sink into a lake of magma. Not exactly a vacation spot. And don't even get me started on the iron worlds. These planets are made mostly of metal, denser than Mercury, with gravity so nuts that even a cup of water would feel like lifting a car. Some of them have cores of almost pure iron, giving them magnetic fields and densities that make Earth look like a feather. These aren't just planets. They're like cosmic anvils forged in a universal foundry. After all this wild discovery, we still haven't found a true Earth 2.0. Even after surveying thousands of stars, no planet perfectly matches Earth's size, composition, orbit, and habitable conditions. The stuff that allows liquid water and life to exist. Which makes you wonder, is Earth rare? Are we the lucky winners of some cosmic lottery, a tiny blue oasis in a desert of extremes? Or are we just not looking in the right neighborhood yet? Current data suggests that Earth-sized planets in the habitable zone, the sweet spot where water can stay liquid, are rarer than we thought. And even if we do find one, there are a bunch of other factors, magnetic fields, plate tectonics, atmosphere, that make a planet truly cozy for life. Bottom line, the universe is absolutely loaded with bizarre worlds, glittering diamonds, molten lava seas, and metallic giants. But a planet like ours? That's still a unicorn. Earth might not just be special because life happens here. It might be special just for existing at all. So next time you stare up at the night sky, remember, somewhere out there are planets that shine like diamonds or bubble like lava. But an actual twin to Earth? That's the real cosmic jackpot. Rogue planets. At a young age, most of us learn that the sun is what makes Earth habitable. It warms our planet, drives weather, and fuels life. That idea sticks. But when you dig deeper, you realize Earth isn't just riding on sunlight. It has internal heat, left over from its formation, powered by radioactive decay, that keeps its core molten and its magnetic field alive. Other rocky worlds can have these heat sources too. Some of us take the rabbit hole a step further, exploring other ways a planet could stay warm. That's where tidal heating comes in. On moons orbiting giant planets, the massive gravity of the parent stretches and squeezes the moon as it travels around its orbit. That flexing generates heat, possibly enough to keep liquid water beneath icy surfaces. This is why moons like Europa may hide oceans under thick ice caps, warm and potentially alive with chemistry. New research pushes this idea even further, to worlds that wander through space completely alone, rogue planets. A paper titled Life in the Dark, Potential Urability of Moons of Rogue Planets by Victoria Froelich and Zsolt Regai explores just how these orphaned worlds and their moons could still support conditions for life. Here, the focus isn't just on habitability, having water or a cozy atmosphere, but urability, a new concept. Urability asks the deeper question, could life even originate there, given the right chemical, physical, and energetic conditions? The universe may be littered with rogue planets, planets that have been ejected from their stars, left wandering the galaxy in darkness. There could be 2 Jupiter-sized rogue planets for every star in the Milky Way. And many of these orphan planets may have moons clinging tightly in orbit. How do we know? The researchers ran simulations of planets blasted free by supernova explosions. Surprisingly, in nearly every scenario, the moons survived, bound to their planets even as they began drifting through the galaxy. The explosions alter the moon's orbits, making them more elliptical, eccentric in astronomer speak. And eccentric orbits mean tidal heating. For some moons orbiting rogue planets, tidal heating could rival that of Europa or Enceladus, potentially lasting billions of years. In other words, a moon orbiting a planet with no star at all could have liquid water beneath its surface, sustained by gravity alone. There could be trillions of rogue moons in our galaxy, worlds we've barely imagined, silently orbiting invisible planets. Detecting them is tough, but with upcoming telescopes like the Nancy Grace Roman Telescope and the Vera Rubin Observatory, we might soon glimpse these dark wanderers. What if the universe is infinite? Right now, the best observations say the universe is flat in geometry. On paper, that means parallel lines never meet and triangles behave like you learned in high school. But flat doesn't automatically mean infinite. It could also mean extremely large and wrapped on itself. Still, let's assume the first case. Infinite. If it really is infinite, the implications are staggering. There's no outside, no edge, no center. Every star, every planet, every galaxy we see is just one tiny speck in an endless cosmic ocean. In fact, in an infinite universe, everything that can happen will happen. Not once, not twice, but an infinite number of times. Somewhere out there, there's a planet just like Earth, someone just like you, reading this exact same script. That's not sci-fi. It's a consequence of mathematics and probability when infinity comes into play. Distances also lose their meaning. Light from galaxies billions of light years away is just a drop in the infinite bucket. Expansion of space doesn't create edges, it just stretches the cosmic fabric endlessly, faster than we can even imagine. Every observation we make is still just a tiny window into an unthinkably vast reality. Here's another kicker. In an infinite universe, the laws of physics we know might still hold, but the sheer scale means anything that can happen eventually does. Weird, extreme, impossible seeming events. They're out there. Somewhere, right now, there could be a galaxy made entirely of antimatter, a star that cycles through explosions and collapses endlessly, or planets orbiting stars that exist in ways our models can barely describe. The infinite universe is beautiful, terrifying, and humbling all at once. It makes our sun, our Earth, our solar system feel tiny, almost accidental, yet somehow part of a grand cosmic tapestry with no beginning or end. Infinity isn't just a number. It's a concept that warps your brain faster than any black hole ever could. What if the universe is a giant loop? What if the universe isn't a straight line from a big bang to a cold, dark end, but a universe that loops back on itself, endlessly cycling through birth, evolution, and rebirth? This is the fascinating idea behind the loop universe, explored in loop quantum cosmology, a theory that combines Einstein's general relativity with quantum mechanics. General relativity describes gravity as the curvature of space-time, brilliantly explaining phenomena like black holes and the expanding universe. But it struggles with singularities, points of infinite density, like the one predicted at the Big Bang. Loop quantum cosmology proposes a solution. Space-time itself is made of discrete loops at the Planck scale, roughly 10 to 35 meters. To put that in perspective, that's a trillion times smaller than a proton. These loops generate a quantum pressure that prevents space-time from collapsing into a singularity. Instead of a true beginning, the universe undergoes a bounce. The energy density at the bounce is estimated to be around 1094 grams per cubic centimeter, an unimaginably high density, but not infinite. This bounce replaces the singularity of classical general relativity and allows the universe to expand into the cosmos we observe today. Current measurements show the universe is about 13.8 billion years old, and its expansion is accelerating at roughly 73 kilometers per second per megaparsec, a value known as the Hubble constant. In a loop universe, this expansion may eventually slow down, reverse, and lead to a contraction, ending in another bounce, a cosmic cycle that could repeat indefinitely. Some clues might already be hiding in the cosmos. The cosmic microwave background, CMB, the afterglow of the Big Bang, has tiny temperature fluctuations of just 1 part in 100,000. Some unusual alignments and cold spots could hint at effects from a pre-bounce universe. While these are still debated, they show that traces of a previous universe might survive the bounce. The implications are mind-blowing. If the universe loops eternally, time may not be linear, but cyclical. Each bounce could slightly alter the structure of matter, energy, or even the physical constants, creating universes that are similar but not identical. The idea challenges our understanding of beginnings, endings, and the nature of time itself. Loop quantum cosmology is more than science fiction. It's grounded in mathematical equations and quantum theory. Researchers are exploring how to test it, looking for subtle anomalies in the CMB, gravitational waves from the early universe, or patterns in the large-scale structure of galaxies. So, when you gaze at the night sky, consider this. The universe might not just be expanding into emptiness. It could be cycling through infinite loops, each bounce a new beginning, each collapse a transformation, a rhythm of creation and destruction on cosmic scales that stretch far beyond human imagination.